Now we're on pages 124 to 133 to finish out this unit. So far we've looked at how temperature relates to the rate of a reaction. Now we're going to look at how concentration relates to the rate of a reaction as a function of time. So during the course of a chemical reaction, the concentration of reactants decrease with time. Rate of reaction depends on the concentration. So if we have rate equals K times A to the first order, the rate of reaction decreases with time because the concentration of reactants is decreasing. Imagine this spontaneous reaction, and suppose that we can't see the product O2. As the concentration of O3 decreases with time, the rate of the reaction will get slower, will also decrease, until the reaction reaches an end and then it will stop. So here is the O3 that we had to start with, which is at its highest concentration, and then the reaction begins, and at the beginning the reaction rate is very fast. However, as time goes on, we have less and less of our reactants, a lower concentration, and therefore the reaction will begin to be slower and slower as it reaches the end. So concentration will decrease as time goes forward in a reaction. The equations that describe the time dependence of the concentration depend on the order of the reaction. A first order reaction, A to B, with a rate law of rate equals K times A to the first order, the time dependence of concentration is given by this rate law equation. The concentration after a time t goes by is equal to the original concentration at the beginning of the reaction, e to the negative K, the rate constant, times the time. If we take the log of both sides of this equation, we would get this one. The log of AT over A0 is equal to negative KT. For a second order reaction with a rate law of rate equals K times A squared to the second order, the time dependence of concentration is given by this integrated rate law equation. 1 over the concentration at time t minus 1 over the initial concentration is equal to the rate constant times the time. This equation also works with partial pressures. Using time dependence to find the order of a reaction. Kinetics data can be tested by graphing the data to see if it fits a first or second order rate law. The equation for a straight line is y equals mx plus b. Recall that m is the slope and b is the y-intercept. For a first order reaction, you could have the equation set up as such, where y would be the natural log of AT over A0, the slope would be negative K, and B would be 0. For a second order reaction, we would have this equation where y would be 1 over AT minus 1 over A0 equals, the slope would be K and T, and the B would be 0. Here is a sample data set which gives the concentration of reactant A at several points in time. So here is time, and at time 0, you could say that this is our original concentration. And then as time progresses, this is our new concentration. So at 5 seconds, the concentration at 5 seconds is 18.196. At 15 seconds, the concentration at 15 seconds is 6.694. The plot of AT versus time looks like this. We cannot tell by simply looking at the data if it fits a first or second order rate law. To find out whether this data is first or second order, the data is plotted in the form of the equations 14.2 and 14.3 above. The data can only fit one rate law. If the reaction is first order, the first order plot will have a straight line. If the reaction is second order, the second order plot will have a straight line. So you would plot based on these two equations, and the one that gives you a straight line is going to indicate the order. So if we graph the above data, and this yielded the straight line, then it's a second order, the data is second order, and not first order since there's a curved line. So if we look at these two graphs, you'll notice that this natural log of AT over A0 is first order equation, and 1 over AT minus 1 over A0 is a second order equation. Because this one yields the straight line, then this is a first order reaction. Since that's a curved line, then that means the data would not be second order. Half-life of first order reaction. The half-life of a reaction is the time required for the concentration of reactant to fall to half of its original value. Look at these data for a first order reaction. Notice that every 10 seconds the concentration falls to 1/2 its original value. For a first order reaction, the half-life is the same time interval over the of the reaction. The half-life in this table of data is T1/2 is equal to 10 seconds because every 10 seconds is how long it takes for the concentration to divide by half. The relationship between half-life and rate constant is given by this equation. The half-life time, which is denoted by T1/2, which is different than just time, is equal to the natural log of 2 over the rate constant. The rate constant for the data set above with T1/2 equals 10 seconds is K is equal to the natural log divided by the half-life. So this equation rearranged to solve for K, and we could get the rate constant for this reaction. So if we take the natural log of 2, which is 0.693, and divide by the half-life, which is 10 seconds, we get a rate constant of 0.0693 seconds to the negative 1. Half-life of a second-order reaction. For a second-order reaction, the half-life depends on the initial concentration of the reactant. The equation for the half-life of a second-order reaction is as follows. The half-life time is equal to 1 over the rate constant times the initial concentration. For second-order reactions, the half-life changes as the reaction proceeds because the concentration, initial concentration, changes. So here's the concentration as it changes as a function of time. And you can see that the half-life for this would be every 2 seconds the concentration would divide in half. Example 14.41, the initial concentration of reactant in a first order, so it's important to note that this is first order, reaction is 0.100 molar. What is the concentration after 4 half-lives? So I'm going to divide 0.1 by 2 4 different times. So here we're going to divide by 2, and that's going to give us 0.05. Divide by 2 again, and that's going to give us 0.025. Divide by 2 again, and you're going to get 0.0125. And we'll divide by 2 one more time and get 0.00625. And so this would be our concentration after 1, 2, 3, 4 half-lives. Example 14.42, the initial concentration of reactant A is 0.275 molar. Calculate the concentration at time t equal to 75 seconds if the reaction follows first order kinetics with a half-life of 17 seconds. So if you want to pause the video here and you can jot down this note card of equations, these are all of the equations having to do with change in concentration as it relates to the rate constant and time. So here are the equations that you need for the first order reactions and here for the second order reactions. So here's the half-life equation. So I'll jot that down, as well as I'll just go ahead and randomly choose. These are derivatives of each other, so I'll just randomly choose one of them and I'll go with this second one. So first off, they tell me that we have a half-life of 17 seconds, and so that requires me to use the half-life equation. I want you to recognize that the only reason you would use this equation is if you're given the half-life, you can get the rate constant, or with the rate constant, you can get the half-life. So let me go ahead and rearrange this to solve for the rate constant. K will equal the natural log of 2 over the half-life, which is 17 seconds. And so when I do this math, I get a K equal to 0.0408 seconds to the negative 1. And now I can use this value for K up here in this equation. Now I am told that the initial concentration is 0.275 molar, and I'm trying to solve for A, which is the concentration at time 75 seconds. So we're going to have the natural log of A, and I'm going to go ahead and add the natural log of the initial concentration to both sides of this equation. And this way I have an equation set to solve for A, negative kt plus the natural log of A0. So natural log of A is equal to negative 0.0408 times the time, 75 seconds, plus the natural log of the initial concentration, which is 0.275. So let's plug that into our calculator. Negative 0.0408 times 75 plus the natural log of 0.275, close parenthesis, is equal to the natural log of A is equal to negative 4.35. However, if I want just the concentration of A, I'm going to have to take E to both sides of the equations. This will cancel out the natural log on the left, and so the concentration of A will be equal to E raised to the, so I'm going to shift and hit my E raised to the, and I'll use the previous answer, which is going to give me a concentration of 0.01289. And so this is the concentration at 75 seconds. Example 14.43, the initial concentration of reactant A is 0.375 molar. Calculate the time required for the concentration to fall to 0.005 molar if the reaction follows second order kinetics. And we're given the rate constant K, which is 4.2. So notice nowhere did they use the words half-life, so I'm not going to be worried about the half-life equation. So it's second order, and I don't need the half-life equation, and so I will use this equation right here. So 1 over the final concentration, which is 0.005, minus 1 over the initial concentration, 0.375, is equal to, I know the rate constant is 4.2, and the question is, what is the time? So I'll go ahead and do the math on the left-hand side first, which will be 1 divided by 0.005 minus 1 divided by 0.375. That gives me this value. And then I'll go ahead and divide both sides of the equation by 4.2, which gives me a time of 46.98 seconds. So here are all the factors that affect the rate of a reaction. Based on the rate law, a reaction is affected by concentration, order, time, quantities such as the activation energy, temperature, sensitivity of a reaction to the orientation and nature of collisions, and the existence of a catalyst. These are all summarized in this figure, that based on these two equations, each of these influences the rate of a reaction: concentration, order, time, activation energy, temperature, the presence of a catalyst, and how sensitive the reaction is to the nature of collisions. Here are two final note cards to consider as it pertains to graphs. If you have a graph of natural log AT over A0 and it gives you a straight diagonal line, then you know you have a first order reaction. If you have 1 over AT minus 1 over A0 and that gives you a straight diagonal line, then you know you have a second order reaction. And this is what they're looking for in the LSU notes. On the AP test, you'll be required to recognize when there is a 0 first or second order reaction. And the graphs are going to be concentration of A, natural log of the concentration of A, and 1 over the concentration of A. So if you get a straight diagonal line with just the concentration of A versus time, then it's a 0 order reaction. If you get a straight diagonal line when you have natural log of A versus time, then that's a first order reaction. And if you have a straight diagonal line with 1 over the concentration of A versus time, then it is a second order reaction.